Hello everyone, this is Orhan Erdem. Welcome to the Linear Regression Theory class. In this class, I will make a very brief introduction to ordinary least squares regression and how we can use it. Let's dive in. Linear regression is a statistical method used to model the relationship between a dependent variable, which I will call y, and one or more independent variables, which I will call x here, by fitting a linear equation to observed dataset. It is commonly used for predicting outcomes, understanding relationships between variables, and identifying trends in data. Let's take a look at this example. Here I have the assessment of home values in the Roxbury region of Boston, which are on y-axis, and their gross area, which are on x-axis. The idea is to find a linear relationship, a linear equation between these two variables. One can guess that the bigger the area of the house, the higher should be the home price, which makes a lot of sense, and that's what we are gonna see. So this chart illustrates my point. I have drawn a linear equation line on my data set. The red line here is the linear equation between the total value and their corresponding area. How can we draw this line? Well, it is drawn based on the idea which is called least squares. So least squares is a method, that's a statistical technique used to estimate the coefficients of a linear model by minimizing the sum of squared differences between the observed values and the values predicted by the model. For example, look at this line. In this line there are 5 data points, each of which is an observed value. And red line is the least square estimated linear equation line, which is y is equal to 1.6 times x plus 0.3. And for every single x, there is an observed value and the corresponding estimated value. For example, when x is 2, the observed value of y is 3, but my line estimates it as 3.5. So that's a kind of 3.5 minus 3, which is a 0.5 residual kind of error. And that residual is negative here, and positive here. So what we do is we take the square of the residuals, sum them up, and find the line which has the minimum summation of these squared residuals. For example, assume that I have these 5 dots again. I have drawn these 3 lines. Okay, the first one is black line, red line, and green line. So which one minimizes the sum of squared residuals is going to be my least square line. So the calculations give the following results. The red line sum of squared errors in the red line is 0.6. Sum of squared errors in black line is 13.45, and in the green line is 2.65. And as you can see, the red line has the minimum squared residuals. That's why it's going to be my best line or my least squares linear equation line. This is my linear least squares equation alone without the other lines. So now the equation of this line is y is equal to 1.6 times x plus 0.3. Well, how do we interpret these coefficients? Let's start with the intercept. Intercept is 0.3. It means this is the value of y when x is equal to 0. So y starts from at least this value. So 1.6 is the amount of increase in y when x increases by 1 unit. So when x increases by 1 unit, y is going to be increasing 1.6 units. So how do I apply this method to my data set? Well, this is the relationship between home value, total value, and the gross area. So if we apply least squares equation, least squares method to my data set using Python or any kind of software, I will end up with this equation. So total value is going to be 303,800 plus 89.3 times gross area. So how do we interpret these coefficients? Again, the first coefficient, which is intercept, 303,800, is the value of houses in the Roxbury region of Boston when the gross area is equal to 0. Which means even if the house does not have any area, this should be the minimum, bare minimum value of the houses in Boston Roxbury region. So we can interpret this as the land value of the houses. How about the slope? So 89.3 is the corresponding amount of increase in the total value when the gross area increases by 1 unit. So if, for example, the gross area is 1,000, so 1,000 times 89, it's going to be 89,000 plus 300, so it's going to be somewhere around $390,000. And that's going to be the predicted value of a house which has a gross area of 1,000 square feet. This is a very generic regression output which I got from Python. The coefficients of the regression equation are given here and R square is given here. So right now, gross area, one variable by itself, is explaining almost 44% of the variation in total value. And the coefficients can be converted into equation like this. So the constant is going to be the intercept here, and this coefficient, the coefficient of gross area, is going to be the slope here. So this is a simple linear equation in which there is only one x and one y. It might be the case that we might want to use more than one feature, more than one input, and that's going to be called a multiple regression equation. So this is the generic form of multiple regression equation. And here I ran a multiple regression equation with two variables. So there is intercept and there is gross area and gross tax. So the coefficients are given here, and I can write this equation as follows. So total area is equal to intercept, almost $41,000, plus 12.85 times gross area, which is the second coefficient here, and 81.18 times gross tax, which is the coefficient here. By the way, take a look at the R square. So the R squares were 44% in simple linear equation. Now I added one more variable. The R square increased to almost 91%, which means that 91% of the variation in total value is explained by just using these two variables. These are two simple examples of linear regression. We took a look at one and two variable cases. So we might have tens of columns and features and millions of rows. So in that case, we should use several other techniques to reduce the dimension and train test splits to test the performance of our dataset and our model. In the next video, I'll use scikit-learn and Python to create more complex linear regression equation models. See you in the next video.